All right, well, welcome to another lovely day of differential equations. It's week 3 already, if you can believe it. We're already a sixth of the way done with this class. After this week, we're going to be a quarter of the way done. Holy crap, that's fast. But anyway, today's plan is we're going to start applying this stuff. We're going to start actually seeing why we care about differential equations, like what's the whole point, like where do we use it and all that. So I'm going to show you some examples today, some that you've seen. I know you've seen like exponential growth and decay, like radioactive decay, but we'll do some others that you may not have seen. We'll talk about Newton's law of cooling. We'll look at like mixture problems, what happens when you've got stuff coming into some sort of a solution. Just sort of start setting the table for why we care about differential equations. So that's my plan. But before we do that, let me turn it over to you guys. Any questions about any of the homework? Anything that we've been talking about so far you want to see? All right, Ralph just gave me a whole bunch here. Let's see. So from 2.2, number 30, and then from 2.4, number 42, and it looks like Victor is on board with that 42 as well. All right, we can definitely look at those. Any others? All right, well, let's go take a peek at those. So I'll go ahead and share my screen. All right, so here we are in 2.2. And wait, we are, yeah, okay, I thought so. So 2.2, number 30. So it says the result of exercise 29 is discouraging, whatever. If any susceptible member of the group is initially infected, then in the long run, all susceptible members are infected. On a more hopeful note, suppose the disease spreads according to the model of exercise 29, but there's a medication that cures the infected population at a rate proportional to the number of infected individuals. Now the equation looks like this. All right, and so it says choose R and S positive by plotting direction fields and solutions on suitable rectangular grids. Verify that if I is any solution such that I of 0 is greater than 0, then the limit as t goes to infinity is s minus q over r, right? Or 0 if q is greater than rs. So blah, 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 blah. But okay, well, what's going on? If you look at number 29, they're talking about an epidemic spreading, a little bit appropriate to the world we're in right now, right? But it's basically just saying that this is the rate of change for it. But in 30, we're going to add a little twist to it. We're going to put in a way to get rid of infected people. Right? We're going to be able to medicate them appropriately, and they're no longer going to be infected. So basically, what I think we should do here is just see if we can solve this guy. Okay. So we're just going to have R and S are positive and see what we get. So let me go ahead and share my whiteboard. I think I got it. Let me just double check. Yep, I think I'm good. And let's solve this guy. Because if we solve it, then we can look and see what's going on when we have our R's and our S's and Q's and blah, blah, blah. All right, so here's our differential equation. Whoops, sorry about that, guys. I'm saying sorry and nothing happened to you. It was just on my screen. All right, so we've got I prime equals Ri times S minus I minus Qi. Now, to solve this, I want you to notice that it is separable. because I can just divide all that stuff over here equals 1. So I've got all of my i's together and all my non-i's together on the other side. So it is separable. Cool. Which means all we got to do is integrate. Now, the 1 is easy. That's just going to give us a t, right? Whatever. Now, this other side, we're going to have to do some work on it. And let me just show you the long way, because this is going to be one that requires partial fractions. I'm going to start by factoring out an I, because notice how there's an I on both of those terms. So we'll have I prime over I times R times S minus I minus Q. And I'm going to distribute and rewrite and everything. In fact, let me, yeah, no, I'll just leave it like this. So we're going to have I prime over I times RS minus Q minus RI. And R, S, and Q, those are all constants. So we don't actually have to do anything with those when it comes to integration time. So then this would be a partial fractions kind of problem. We're going to have A over I plus B over RS minus Q times or minus RI. So when we combine that, we're going to get A times RS minus Q minus RI plus BI. And that has to equal 1. So if we let say I equals 0, that all goes away. We get RS minus Q times A equals 1, or A equals 1 over RS minus Q. And then the other I would use is RS minus Q over R. So when I plug that in here, that gives me 0. So I get B times RS minus Q over R has to equal 1. So B is equal to R over RS minus Q. So if we take that and bring that back here, we now have, excuse me, 1 over RS minus Q times, well, the A was 1, so 1 over I, plus B over all this stuff. Well, there was an R, RS minus Q minus RI equals 1. Oops, I prime. All right, so now we're ready to integrate. So integrate both sides. Oops, that was supposed to be over there. We're going to get 1 over RS minus Q times the natural log of I plus the natural log of R times the natural log of RS minus Q minus RI divided by minus R. Make that a minus. And then that's all going to equal T plus C. And I don't remember if there was an initial condition. Let me just go back and look real quick. Yep, we had I of 0 equals I naught. So let me go back here. So we had I of 0 equals I naught. All right, well, we're going to go ahead and find our C, but first, let's simplify this a little bit, because I can combine these into one log with division. I'm going to multiply the RS minus Q over here. Then I can run the hook. So I get this exponential. How about not E equals? How about that fraction equals? So I over RS minus Q minus RI equals E to all of this stuff. And now we can plug in 0. So we're going to get I naught over RS minus Q minus RI naught equals, well, if that's 0, then we're going to get some new C, because this is going to be E to a bunch of garbage. So we're almost there. So if we multiply stuff over and combine, we're going to get I naught equals Q, or sorry, RS minus Q not I naught equals C equals. Man, my brain is like a half step behind today. Oh, never mind. There's our C. It's already there. So, oh my God. Okay, but that C is actually a multiplier on this. So once we get there, man, we have I over RS minus Q minus RI equals I naught over RS minus Q minus RI naught times E to the RS minus Q times T. Whew. Which we then could solve for I and do our thing, right? So we can get the solution. It's not pretty. It's got exponential stuff in it, but we can definitely get our equation. Which, if we go back and we look at what it asks us to do, right? Well, whoops, too far. It said plot direction fields. Okay, so we can choose an R and an S, put in the numbers. R equals 0.5, S equals 1,000, you know, whatever we want. And then we can kind of plot it. But then when it says do this, then it says find the limit as t goes to infinity. And it says there are 3 cases to consider. So let's come back and look at our thing and see why there are 3 cases to consider, and they're all about RS, right? It's Q equaling RS, being more than RS, and being less than RS. So let's come back here and let's see why that matters. Okay, so first of all, just notice if Q is equal to RS, then this stuff in the parentheses goes away. And we get a very different structure for this equation. I got space over here. Okay. So if we have Q equals RS, and you go back to this original differential equation, Q minus RS is 0. So it becomes I prime over minus RI squared. And this one, when we integrate, Notice that it doesn't give us natural logs at all, because it's just I to the minus 2. So we get I is equal to 1 over R times T plus C. And look at what happens to that one as T goes to infinity. What's that going to do?
It goes to 0.
Yeah, it's going to go to 0, regardless of what R is. And the C obviously is going to be related to I naught. So, and we could find that using the initial condition. But we know that one's going to drop off to 0. Okay, so that's what happens if Q is equal to RS, because it even has a different derivation. If Q is greater than RS or less than RS, then we still use this derivation. But let's look at what we get down here with the E business. And let's look at what the difference is. So there's our RS minus Q. But specifically, you look at this piece. What's going to happen to this? Let's do the RS minus Q is greater than 0. What's the limit as we go to infinity? So this thing in parentheses is positive. What's that going to do?
It's going to increase without bound, right?
Okay, so this, yep, so this exponential piece is going to go without bound, which may or may not cause us to go to infinity, depending upon what happens when we solve for I. Right? So there's still a little bit of work we got to do, but notice that if that happens, then this piece goes to infinity. What if it's less than 0? If that guy's negative, that's going to drop to 0. So depending upon what your, what you get when you solve for I, those exponential pieces are going to do complete opposites. It's either going to grow without bound or drop to 0. And so that means that your limit's going to do one of two things. It's either going to grow without bound, or it's going to, approach something else where the thing goes to 0. So you still need to solve this for I. I was trying to be lazy. Let me just solve it for I. Let's just get rid of all this stuff, make some space for us real quick. And don't worry, you can always come back and look at the video and catch any steps that you missed. And you can also critique my form and see where I went wrong, because I'm sure I'm going to go wrong here somewhere. Okay, so if I get rid of that fraction, I get I equals, I'm just going to call it e to the stuff, if you guys don't mind. So we'll have RS minus Q minus RI times e to the star. Okay, the star is all that stuff. We'll put it in at the end. So I need to distribute and then move that RI piece over here. So I get R or I plus RI e to the stuff equals RS minus Q times e to the stuff. Factoring out the I. Which then gives me I equals RS minus Q times e to the stuff divided by 1 plus R e to the stuff. I'm going to divide everything by the e to the stuff. I get RS minus Q over e to the negative stuff plus R. Okay, so now let's look at the two cases. So if we've got the RS minus Q is greater than 0, so this is positive, which means this is a negative exponent. which means this goes to 0. Our limit is RS minus Q over R. So S minus Q over R, just what that's going to end up being. If we go and we look at the other possibility, let's do that up here. Let's look at the RS minus Q is less than 0. So if that's negative, negative is a positive. So we get e to the positive infinity, which makes that denominator infinite. RS minus Q then, when I divide by infinity, goes to 0. So you get very different result. You get a very different long-term approach, depending upon which side of RS minus Q you're in, or which side of 0 that's in. So let's go back and look at the question again, what all those different things are, R, S, and Q. So let me just go up a slight bit. So R was the infected rate, or basically like an infected proportion. S, this is a number of susceptible people. Okay, so that's a maximum number of susceptible people. And then Q was how many people were removing from being sick. So let's think about this. Oh, hey, look. Verify that the limit is Q, S minus Q over R. I think we found that. And then, oh, the limit is 0 if Q is greater than or equal to RS. So we actually found what we needed to show, which is nice. But if you think about why this is, okay, so Q is less than RS. RS is basically how many people are getting infected. Q is how many we're removing the infection from. So if Q is less than RS, then we're not able to keep up with the infected rate. Like people are getting infected and we can't counter it as much. If Q is greater than RS, we're curing more people than get infected. And that should make sense that eventually then, oh yeah, we'll have everybody cured because we're curing more than those that are getting sick. The Q equaling RS just means that we are curing as many people as get infected. But it just turns out that in this case, that's enough for it to still drop off to 0. But the nice thing here with even though our Q is less than RS, so we're curing fewer people than are getting infected, it at least isn't growing without bound. Right? It's just going to end up equaling S minus Q over R. So it's not growing without bound, and we're not going to get so that everyone who's susceptible gets it. There are always going to be fewer people depending upon what that Q over R is. Anyway, not that I'm an, epidemiologist or anything, but I know how the math works. I know how the numbers work. And this is why I was very quick to be vaccinated when I had the opportunity for COVID-19, because think about it, that's what's going on here. When you vaccinate, just run, if we want to talk about the numbers in the context of this, it actually does two things, right? The curing, I don't know that we're necessarily curing, but the vaccination rate is like increasing our Q. And increasing the Q is good, right? Because if the Q gets big enough, then it'll drop to 0. But the other thing the vaccination does is it changes S, changes the number of susceptible people. Because if you go and you get vaccinated, now, granted, it's not 100%, right? Like we know that the efficacy is not 100%, but we are removing people from the S. There are fewer in our susceptible population, which means we're lowering the transmission rate, the R times S, right? So vaccinations are like a twofold. They increase the Q and they decrease the RS. So if we come back to this guy right here, right, we're increasing Q and we're decreasing RS, which means in vaccinations, you're kind of bringing those two things closer together so that eventually Q can get bigger than or equal to RS. So that's the math actually behind things like immunization. That's why they do what they do. And I think because I'm a mathy, sciencey guy, I see that and I see the numbers and I'm like, well, what the hell? You give me a vaccination. Not only did I increase Q, but I lowered the RS. Hell yeah. That's a win-win, right? Just for a little bit of stiff arm and kind of tired for a day. It's well worth it, in my opinion. I'm not saying you should go get vaccinated, but mathematics says you should. So if you believe in the math, you should do it. Anyway. So was that better for number 30? Kind of see what we needed to do there. I think that Ralph, you were the one that asked about it. Better? Okay, cool. Get a thumbs up from Victor too. I love it. All right, so let's go look at number 42 from 2.4. Jump to that a little bit faster. Okay, so 42 says use the method suggested in exercise 40. Okay, to solve the given equation implicitly. So if we look back at number 40, it just says that if AD minus BC does not equal 0, would that just make you think? And I should pick on Victor because he's the one who always says it reminds him of linear algebra.
Yeah, linear, the determinant.
Yeah, determinant of a 2x2 matrix.
Mm-hmm.
Oh, guess what? Yeah, this is something to do with that. If you look at it algebraically, solving that system. Anyway, let's start to draw and everything. Do that. Okay, so we got y prime equals this. We can transform it into the homogeneous nonlinear equation, looking like that guy, with this substitution. Okay, now, I didn't say you needed to prove it. We're going to just use this method to see if we can solve it. So let me go ahead and write down the equation here. So 42 is 2x plus y plus 1 over x plus 2y minus 4. And so we're trying to turn it into the homogeneous, but not homogeneous as we originally meant homogeneous, nonlinear equation. So we're going to get a times x plus b times y, c x plus. Okay. So now I got my numbers. Let's go to the whiteboard. All right. So here's our differential equation. We have y prime equals 2x plus y plus 1 over x plus 2y minus 4. So first things first, we should make sure that we meet the condition, right? Remember it said we needed to see that AD minus CB was not equal to 0. So let me come back, I'll show you that, right? So AD minus BC does not equal 0. So let's go back to our problem and check that with the AD. Actually, we can do it right here. So A times D is 4, B times C is 1, 4 minus 1 is 3, not equal 0. Okay, so we confirm that. So we know that we can use this. So we want to turn this into a y prime equals 2 times x minus x naught plus 1 times y minus y naught over 1 times x minus x naught plus 2 times y minus y naught. Right, so that's what they were saying. If AD minus BC does not equal 0, we can do it this way if we choose our x naught and y naught the right way. Okay, so I guess the question is, what do the x naught and y naught have to be? How are we going to be able to answer that?
Do we take the partial of the original one with respect to y and x?
We do not need to take the partial just to find that.
I guess we need a system of equation.
Yeah, we just make the system of equations. This is going to, so you look at the top, you have 2x minus 2x naught plus y minus y naught. That needs to equal 2x plus y plus 1. So we know that minus 2x naught minus y naught has to equal 1. And then do the same thing on the bottom. You're going to get x minus x naught plus 2y minus 2y naught. So that's minus x naught minus 2y naught equals minus 4. So we got ourselves a system. So let's go ahead and solve it. So x naught here is equal to 4 minus 2y naught. Fire that up there. You get minus 8 plus 4y naught minus y naught equals 1, which looks like y naught equals 3, which means x naught equals minus 2, I think. So that means if we go back to this guy, we have y prime equals 2 times x plus 2 plus y minus 3 over x plus 2 plus 2 times y minus 3. Okay, so all we did right here was get it into the form that we needed so that it's now homogeneous in the new definition of homogeneous, not the original equaling 0 definition. Real quick, this is why the AD minus BC can't equal 0, because you have to be able to find a solution to the system, right? Which means if you make the coefficient matrix here, it's got to have a determinant, or it's got to have an inverse. So its determinant can't equal 0, and its determinant equals 0 would be the AD minus BC equals 0. So that's where that came from. Anyway. Now what we need to do is turn this into the new form of homogeneous. So what did the new form of homogeneous look like? What did it mean if we had an equation that was homogeneous but not in the old way of calling it?
Just y over x.
Okay, we had to have it as a function of y over x. So the way that we're going to make that look like this, or make this look like that, I should say, is we're going to multiply top and bottom by 1 over x plus 2. So if we do that, this looks like this. And now we've got that form, y over x. Now, I know it's not exactly y over x because it's got the y minus 3 and the x plus 2, but those aren't going to affect it in terms of that, because this is where kind of you do the u sub kind of deal. And you go, well, what if we call big Y little y minus 3? And big X will be little x plus 2? Because the derivative of big Y and the derivative of big X is the same as the derivative of the smaller ones. Those constants don't do anything. And so now we're in that y over x form. Okay, so is that far enough for you on this one, or do we need to go and finish it off? And I'm going to specifically ask Victor because he asked about this one. Oh, I guess Ralph did too.
I'm fine with this.
You're good with this? How about you, Ralph? You're good? Yeah. Okay. So now that you're at this point, okay, you follow the techniques for the new termed homogeneous ones, and you're good to go. So it's a nifty little trick, but again, are you getting tired of hearing the same thing every time? Right? Like I was about to say, it's the broken record, not that you guys know what that means, although vinyl is making a comeback. But it's just skipping, and it's like, okay, we just hear the same thing every time. Hey, look at it, here's a trick. Here's a trick. Here's a trick. It turns into a form we already know. It's a form we already know. Use this trick. So that's the moral of the story with DiffyQs. Just learn the tricks. And I'm going to introduce you to lots of them. We've already seen a bunch. All right. So there you go. So is that good for homework? Feeling okay in general? Hopefully you're just seeing that it's, same thing over and over and over and over and over. All right. So let's talk applications. We got about an hour. So let's start doing and talking about some of the applications of differential equations, where we see them and why we care. All right, because I know for most of you, you're not taking this because you're like super into math, like you don't mind the math, but you want to use this. You want to use this when you're programming computers. You want to use this when you're building bridges. You want to use this when you're doing whatever physics or engineering, right? When you're studying the stars. So let's start talking about where we use differential equations. So I'm going to go ahead and share my whiteboard. I think I'm just going to stay at my computer today instead of just bouncing around. So let me just start with some examples of differential equations that I know that you've seen. Okay, so these are where we use them. Okay. So where do we see differential equations in quote unquote real life? Now, I still like to put this in quotes, the real life, because some of these are still oversimplifications. We are able to do more with this, with what we've got, but there are still limitations that we apply. There's still assumptions that we make, so that they're still in a nice enough form. Okay, but these are definitely more real world than other places. So let's just start with exponential growth. So you all know about exponential growth. You've seen it. We've used it in various places. Some of the real world topics we talk about are populations, population growth, money grows exponentially, and so on. But the key to exponential growth is always that the rate of the change in the population. And I'm going to use the word population, even though I don't necessarily mean like people or animals. So if we're talking about money in your bank account, there's a population of money. It's the balance, right? Or whatever. But the key is that the rate of change in the population growth, or rate of change in population, is proportional to the population. So basically, this just says that the bigger the population, the bigger the rate of change. And that's why this works really, really well when we talk about population dynamics. Like, let's say one of the populations we're talking about are the coyotes that are in Lake Tahoe Basin. If there are more coyotes, they will breed more and have more little coyotes. If you double the number of coyotes, you double the number of offspring. If you triple the number of coyotes, you triple the number of offspring in general. Again, we're making that assumption that it's nice and smooth and continuous, where in the real world, clearly it's not, but we're going to try to model it. It is. Same thing happens with your money. If you double the amount of money in your bank account, you're going to double the amount of interest that you earn. If you cut the amount of your bank account by 1/10, you're going to earn 1/10 as much interest. So in that kind of scenario where you get a rate of change that's proportional to the population, that leads to exponential growth. Now, this also gives us a differential equation, right? The rate of change, y prime, is proportional to the population, y. So for exponential growth, it leads to a really simple differential equation. Y prime equals k times y. Boom. Okay, now, what kind of differential equation is this? Classify it. Give me all the words you can that you know that describe it.
First order and linear.
Okay, I like first order. I like linear.
Separable.
It is separable.
It's kind of cute.
It's kind of cute.
Non-homogeneous.
Okay, so non-homogeneous actually is incorrect. It is homogeneous, because remember the form for homogeneous is, for linear, is if you put all those y's together, it actually does equal 0. So it's linear, first order, homogeneous. It's also separable, right? Separable, first order. But regardless, this is one that we can solve. And let me actually show you the solutions both ways. If we were to separate it, change color here, so right over here, you get y prime over y equals k. You integrate, you get natural log of y equals kt plus c. So y equals e to the kt plus c. That plus c as an exponent can come out front as a multiple c. And so if we separate it, we get y equals ce to the kt. Well, let me show you what we get if we do it the linear first order homogeneous way. So here, p of x is, or I guess p of t. I'm going to erase that since I use t on the other side. And just so you know, it's pretty much standard to use t as your variable when you're talking about populations or exponential growth, because it's usually time dependent. Anyway, so p of t is negative k. So then the solution is going to be e to the negative integral of negative k. So negative negative is positive, so we get y equals e to the kt plus c, which, hey, look, it's exactly the same thing. So either method gets you there, but it's a pretty quick and easy one to solve. And I guess, yeah, we'll go ahead and say it's a cute little differential equation. All right, so this has so many uses, I can't even tell you all of them, right? So population modeling, money, but anytime you've got a situation where your rate of change is proportional to the population, you get exponential growth. Now, a complement to this one is exponential decay.
Real quick, isn't this
Yeah.
per formula?
Yeah, this is
PERT?
exactly PERT. Yeah. I just wrote it as C and K instead of P and R. But yep, that's where that comes from. Pretty crazy, huh? So exponential decay, this is the same as growth, except for what we're going to do is the rate of change is a negative rate of change. Because instead of growing, it's going to be decaying. But if you think about this, so the place where we tend to see this the most is with like radioactive decay, right? We're looking at, carbon-14 or something and looking at how much is left or whatever. If you double how much carbon-14 you have, you're doubling how much of it decays, goes away, right? If you have 1/5 as much stuff, you lose 1/5 as much as if it hadn't been there. So its rate of change, which in this case is a negative change because it's dropping, is still proportional to the population, to how much is actually there. So at the end of the day, what that means is that you get exactly the same formula. It's just K is negative. So exponential growth and exponential decay, they're really the same thing. It's just the rate of change is either positive or negative. So you get exponential growth or exponential drop off. Now, for any one of these in a real world problem, you're going to need to figure out C and K. All right, so some things to know about C. So C, this is the starting amount. Okay, whatever that C is, it's basically Y0. So if you're told how much you started with, cool, that's your C. You're done. Okay, now K, this thing is a growth decay rate. And sometimes it's given to you. Sometimes you're told exactly what it is, but sometimes you have to figure it out. Well, if you have to figure it out using information that they tell you, this is when you're going to have to potentially use a system of equations. Okay, so don't be surprised if at some point you probably need a system, because you might not know either of them, right? Like, for example, let's say we're looking at a radioactive decay kind of thing, and we don't know how much we started with of a material, but we know how much of it was there in 10 years and how much was there 20 years. Like let's use Chernobyl as an example, right? So like Chernobyl, which is over in Russia, I'm sure you guys all know about it, but it was a huge nuclear reactor that had a meltdown, major problem, and the area around that facility is still radioactive, but you can actually go tour it now. I wouldn't do it. I wouldn't do it. The amount of stuff that's still in there, that's in the dust and everything else, like, ugh, I wouldn't do it. I wouldn't
Isn't
do
it going to remain uninhabitable for like the next 20,000 years or something?
something like that. Yeah, like it's nasty. A lot of the stuff that was there, really nasty. But anyway, so here's the deal. Do we know how much material was there of the various radioactive types? Kinda. The Soviets were really hush hush about it though, because, well, the Soviet Union didn't share anything. So we don't really know, but we've been able to go and take measurements subsequent, right? And we know exactly the day that it happened. So we know exactly how much time has gone by. So we can say, hey, you know what? 10 years after the fact, here were our levels of strontium 90. I'm just throwing something out. I don't even know if that stuff's there. And then 20 years later, here were our levels of strontium 90. You have two YT values, two data points. Well, you can put those into this equation, get your two equations with your two unknowns of C and K, and you can find C and K, right? So a lot of the time, you're going to have to use a system to figure out what those two things are. However, specifically with radioactive decay, I want to mention half-life, because that's a biggie, right? You guys all know about half-life. Well, half-life, the nice thing about that is you can get your K really easily. And let me show you. Okay, so let's just say we're going to let big T be the half-life. So that means that whatever we started with, which was C, is how much we're going to be left with after that half-life. Right? C was my starting amount. At half-life, half of it's gone. So I can divide those things both by C. It goes away. Now I can take my natural logs and I can actually solve for my K. And so if you're given a half-life, you're going to know that your K, your decay rate, is the natural log of 1/2 divided by that T. And notice that this will be negative because natural log of 1/2 is negative. So regardless of what your half-life is, your K is going to be negative, which leads to decay. So that one's just so important, so commonplace, that I figure it's worth just noting. That way you don't have to solve the system ever. It's natural log of 1/2 divided by the half-life. So the longer the half-life, the smaller the K, which should make sense. Because if it takes longer for it to decay, that decay rate needs to be smaller.
So when we say smaller, we mean closer to positive, right? In this context?
Yes.
Okay.
Closer to 0.
Yeah. Okay.
Yes.
Just making
Yes.
sure.
No, you're right. And that's technically I should, yes. Yep. Okay, so you guys have seen those. I don't know that I really need to show you more examples, but I just wanted to show you how, the cute little differential equation, as Victor says. All right, so yay, you've seen those. But let me show you some other ones that are related to exponential growth. These are similar. Let me show you real quick the logistic model, and we'll talk more about this in a later section when we talk about autonomous differential equations. But for a logistic model, this is exponential growth, but with a carrying capacity. So I'm going to put here with a maximum population, sustained population. Now, this makes it more real world. Like if we're going to talk about the coyote that are living in the Tahoe Basin, we can't have an infinite number of coyote. It doesn't happen. They run out of space. They run out of food, right? They're hunted more or whatever. Like there is a limitation. And it's not just coyote in the wild. I mean, anything. I mean, there's a maximum number of humans that can live on Earth. Right? At some point, there's not enough resources or whatever. So there is a maximum. So in situations where you want that, this leads to the logistic model. So first of all, the name of this maximum sustained population, we call this the carrying capacity. And I'm going to use the letter L. I'm not sure what the book uses, but I'm going to use the letter L. So here's what changes in that differential equation. We still need to have exponential growth. So we still need the cute little y prime equals ky. But now we're also going to multiply by an L minus y. And I want you to think about the consequences of this second part. Because that's different, right? The ky, we know what that does. That's making it grow exponentially. But what happens when we have an L minus y that we're attaching to it? Well, let's just start with, what if we're at the carrying capacity? What if y equals L? What happens here?
It's all 0.
Okay, yeah, so if y equals L, that tells us y prime equals 0. So what does that tell you about the population?
It's constant.
Constant. Doesn't go up, doesn't go down. We're at the capacity, we're just there. Okay, so that makes sense. What if y is bigger than L? What happens to L minus y?
It's negative.
That guy's negative, the ky is still positive. So we get y prime is less than 0, which means that the population decreases. So this is in here so that if we get bigger than our carrying capacity, the population is going to drop off. The coyote are going to die. There are too many of them. They're going to die from starvation or whatever else. Okay, and then if y is less than L, this is now positive, everything's positive. So our population is going to be increasing. So notice that just by introducing that L minus y, we made it so that it's still going to grow if we're less than the carrying capacity. We're going to die out if we're greater than it. So this is the easiest way to take care of that. Now, I'm not going to solve it yet, keyword yet, but I want you to think about this. Where was I going to go? Oh yeah, so classify it. Like if you're going to solve it, how are you going to do it? But let's start with classifying. So again, it's first order, right? Is it linear?
No.
No, not anymore. Right? If you were to distribute that out, you get a y squared. So we can't use linear methods. Is it separable? Hopefully you can see that it is separable. Because all you'd have to do to separate it, you could write it as y prime over y times L minus y equals k. So this guy is separable. It's going to require doing a partial fractions kind of thing, and we'll do this later. Okay. But what I want to show you is what the result of it looks like. So if you were to actually draw the graph, obviously it's going to depend what our initial condition is, but let's say that this is our carrying capacity L. But what you're going to see is, let's say we start down here with whatever this is our initial population. It's going to grow kind of exponentially, but then it slows down and flattens off. And you can see that the closer we get to L, the smaller this is. And we can use smaller in both cases here. It's not only smaller, but also closer to 0. So y prime, the growth rate slows down as we get closer to L. Anyway, we'll figure out what the equation of this looks like later. But by making it more realistic, throwing on the sustain, a maximum population, it made the differential equation a little bit uglier. And it also meant we had to use separation. It's no longer just linear. All right, so that's the logistic model. Now, this is still a simplification of populations. So if you wanted to get really crazy, I don't know that there's a name here, but we could also add in a threshold. And what the threshold is, what I mean by that, is this is the minimum needed to propagate the species. All right, so it's going to be a number that if we dip below it, the population is going to die out. And this is very real. When we talk about, say, endangered species, their numbers are so low that if we're not careful, they will no longer exist anymore. Okay, well, let me show you what happens with that differential equation. So we'll call that, say, big T for our threshold. So again, we're going to have our y prime equals. There's going to be exponential growth. There's also going to be the, well, L, hold on. Don't know where that T came from. L minus Y, because we'll assume that there's still a carrying capacity. Does that make sense? But now we need to put in a y minus t. And notice that this is going to do the same sort of thing that the carrying capacity did. Like when we look down here with the different y equals, we can do the same thing with t. And now we can say, well, if y equals t, again, we get y prime equals 0. So we're just constantly at that threshold rate. If y is greater than t, y prime is positive. So our population is going to go up. If y is less than t, y prime is negative, and we're going to die out. So what would change on this graph is now there's going to be a t value, so that if you ever get below t, it drops out. If you're above t, it's going to grow kind of exponentially, logistically, towards your limiting value. If you're greater than L, it's going to drop back down. Right? But now, one more bit of complication. Turns out that this thing is still separable. You could rewrite it as y prime over y times L minus y times y minus t equals k. So you can integrate it. It's still a partial fractions deal. It's just more. It's more complicated. Okay, well, anyway, so I know for a lot of you, you're like, right, this is population modeling. I don't care about population modeling. This is silly. I'm a physicist engineer. Let's get back to some of those. All right, well, another example of where differential equations comes in is Newton's law of cooling. And this is another one you may have seen before. For those of you who took physics with me last year, pretty sure we talked about this a little bit when it came to the thermodynamics. We didn't actually solve the equation. Well, we might have, I don't know. All right, but here's how Newton's law of cooling works. Basically, the idea behind this is the rate of change in a temperature it's proportional to the temperature of the environment, or to the temperature difference to the environment. So if your temperatures are very similar, so the room, let's say the room, and for those of you who are not, I'm going to use Kelvin just because. So if the room is 293 Kelvin and our cup of coffee is 300 Kelvin, they're pretty close to each other. And so there's not going to be a real quick change in temperature. But you take that same 300 Kelvin cup of coffee and you put it in 275 Kelvin environment, which is barely above freezing, the rate of change is going to be much faster. Okay, so the rate of change in temperature of an object is proportional to the difference in the temperature of the object and the environment that it's in.
I've heard of it described as like a temperature gradient before, like it's proportion, like the rate of change is proportional to the temperature gradient.
Yep.
Is that term like similar to the one like used in calculus in terms of gradients, or?
Yeah. So just think gradient is slope. So a gradient is a slope or a change, right? And
Yeah.
so when you say that you heard it as it's proportional to the temperature gradient, that's the change in the temperatures between environment and object. So it's
That
not
makes sense.
exactly the same, because in calculus, when we say gradient, we're specifically talking about a vector that comes from a vector field, right? But it's the same kind of idea. All right, so check it out. Here's how this plays out then. The rate of change in the temperature of an object is proportional to the difference in the temperature of the difference to the environment. So I'm going to write here T minus T sub E. So the T sub E, that is our environment's temperature. So I'm setting it up exactly the same way, right? Rate of change, T prime, is proportional to K times the temperature difference to the environment, T minus TE. Okay, but there's a bit of a problem with what I have written, or at least something we have to worry about here.
What unit for temperature you use?
Okay, so one of them that we definitely should be careful about is what unit of temperature we use. Turns out that it's going to be okay, whichever unit you use. You're just going to get your K values are going to be different. So, you know, like there's going to be a difference with Celsius versus time versus Fahrenheit versus time versus Kelvin versus time. The difference between Celsius and Kelvin is not an issue. because the linear relationship between them, that it's just, you know, plus 273. Because think about that, when you differentiate, adding an extra 273 doesn't change your rate of change. So that one's not as big of a deal as if you use Fahrenheit. Don't use Fahrenheit. For the love of God, don't use Fahrenheit. Because now you're going to be off by a factor of 9/5 or 5/9, and it can get kind of ugly. But that's not actually the issue that I was going with, but it's definitely something to pay attention to. I default to Kelvin when I'm doing thermodynamics, but there's an issue with this equation. Just as written, there's a problem with this equation.
I'm thinking if the T is equal to TE, you're going to get 0 and temperature can't remain constant.
Okay, so let's definitely think about that T equaling TE and like either side of it. So TE is the temperature of the environment. And we're going to assume actually that that is constant, that the temperature of the room, let's say, is not fluctuating, which is a big assumption, right? I mean, you think about the room that you're in right now, like you are warming up the room just by being in it, right? The different chemical reactions in your body are exothermic. You're producing heat and it's going out into your room, right? But let's assume that the environmental temperature is constant. So let's just go there. So what happens if the temperature of your object, so here's my ice cold root beer. It's out here in the room, and I'm even trying to insulate it a bit, right? Got my nice little Virginia Institute of Marine Science koozie. Yeah. So I'm trying to keep it ice cold, but it's not working. It's definitely warming up. But let's say it eventually reaches the temperature of the environment. Is its temperature going to change anymore? I mean, the formula says no, because if T equals TE, right, if we look at that, that's going to be 0, so T prime equals 0. But does that make sense physically?
No.
No? So the temperature of this can of root beer is the same as room temperature. How's it going to cool down?
It won't.
Okay, how's it going to warm up?
I guess it won't.
Yeah, there's no heat source or anything because it's at equilibrium. So that's actually okay. And that's good. That if T equals TE, that T prime equals 0. That's really good. I want that because that's thermal equilibrium. Okay, so let's see what happens if, say, T is greater than TE. Because let's think about what should happen. So now I've got something warmer than the environment. So not my ice cold root beer, but a nice hot cup of coffee. Whew. You can tell I'm not a coffee drinker because I can't even say cup of coffee, where ice cold root beer just flows off the tongue. Anyway, all right, so I've got a hot cup of coffee. What's it going to do?
It's going to heat up the environment.
Okay, so it'll heat up the environment nominally. What's going to happen to the coffee?
It will cool down a little bit.
Okay, it's going to cool down a little bit. And in fact, eventually, like if we go to infinity, it will cool off to room temperature, right? And if you're not a coffee drinker, it doesn't really matter. Just think about anything you take hot, your hot slice of pizza out of the oven. You set it on the counter, you forget about it, and you come back to it the next morning. What's the temperature of that pizza?
Cold.
It's cold. It's the temperature of the room, right? So if it's hotter, that's what we're saying right now. If it's hotter than the environment, it should cool off. Well, what does our differential equation say? If T is bigger than TE, what's in the parentheses is positive. which means my temperature should be increasing. And this is when you should just yell at me in all caps. No, that's not right. So what do we have to do to it? What do we have to do to this equation to make it so that it'll actually be negative instead of positive?
Do something with K.
Yeah. In fact, what we're going to do is, how about we just make it negative? If all you want to do is change the sign, well, that'll do it. So now this is actually less than 0, which means we're decreasing, which gets as enthusiastic a yes, that's better. And let's just double check, what about if T is less than TE? So that's our ice cold root beer. It should be warming up. Its temperature should be increasing. And we see that now because this is negative times a negative is positive. So even though it is just due to the temperature difference in the environment, well, we need to make sure that we're finding the difference the proper way. So what you'll usually see though is they'll distribute that minus sign through. So you get T prime equals K times TE minus T. It's still the difference. It's just we're taking the temperature of our object and removing it or taking it away from the environment's temperature.
So that makes sense because when you asked us, like, what do we need to take into consideration when I said, what unit we use, because I thought of negative degrees Celsius and saw that it would have been positive. I'm like, that makes no sense. But that minus K fixes that.
Yeah, and it also makes it so that we're literally only looking at the difference in the two. So, I mean, even if we've got a negative temperature, it's still going to be off from another temperature just by the subtraction, So it's kind of nice that it doesn't actually matter. Everything will work out. Just don't use Fahrenheit because Fahrenheit's a bullshit scale. Yeah, I said it. I'm on record saying it. I'm quite certain I'm on record saying it in other classes too. Okay, well, so here's that differential equation. We need to solve it. Well, check it out. It's linear and it's first order. It's just not homogeneous, right? If I multiply this through, move the KT over, I get T prime plus KT equals KTE. Now remember that the TE is a constant. That's the temperature of the environment. So we can easily solve this linear first order. So since it's non-homogeneous, we start with a Y1. So this is a little t now instead of the big T for temperature. So that's e to the minus KT. All right, so then what do you do? Once you get your solution to the homogeneous, how do you get your solution to the non-homogeneous?
I would need to find U.
Okay, how do you do it?
The integral of would be KT over e to the U, e to the negative KT.
Okay. All right, so the K and the TE, those are constants, so you're going to bring those out. So KTE times the integral of e to the KT. Cool, well, that's just going to give us e to the KT plus C. The K's canceled here from U substitution. So then we multiply that by the Y1. So we get T equals, well, if I multiply this by e to the minus kt, I get TE plus CE to the minus KT. So it was super easy to set up and actually not terrible to solve. I mean, obviously we still have to figure out what C is, but that's going to come from our initial temperature, right? And in fact, if we, let's just go ahead and do that. Let's say that we've got the T of 0 equals, we'll call it T naught. Then C is equal to T naught minus TE. So we'll go ahead and put that back in here. Then we get T equals TE plus TO minus TE, e to the minus KT. And so there you guys go. That's the formula for the temperature of any object. So if you know the environmental temperature, it's TE. You know its initial temperature, T naught. The K, that's just going to come from the thermodynamic properties of the object. If it's something that allows for heat transfer, a quick heat transfer, then that K is going to be big. If it's something that's very well insulated and doesn't allow for much heat transfer, then that's going to be small. But regardless, think about what's going to happen as T goes to infinity. As T goes to infinity, this piece, e to the minus KT, goes to 0. And so we get the environmental temperature. So if you come back to my ice cold root beer and the idea of the koozie, right? We put it in the koozie here to help change the K. We're trying to lower the K so that it doesn't lose its temperature as quick, or it doesn't gain temperature as quickly, right? It's an insulator. And that's the whole point of insulators. That's why coolers are designed the way they are, to help keep it so the ice stays ice and so on.
So would K be like specific heat or boiling point?
So K,
Or does it
it's
just
actually, it's actually, it's more related to specific heat, but it's not exactly specific heat, right? Because specific, if you think about what specific heat is, that's how much energy you need to change the temperature. But it's not talking about how quickly that energy is transferring from one to the other, because there's no rate involved in it. But it's definitely related to that. It's not related to the latent heats. So like you're talking about the boiling point and all that, right? So you think about the latent heat of fusion or vaporization. That is energy that doesn't change temperatures. So it doesn't apply here in Newton's law of cooling, because Newton's law of cooling, you have to have temperature change. So anyway, but there you go. It's a pretty straightforward calculation. Now I did this using the linear first order stuff, but we could have done it with separation. Right? I don't know if anybody saw that, but some of you might have gone, well, wait a minute, you can separate that thing. Let me just show you really, really quickly down here. If you separate that, you'd have T prime over TE minus T equals K. So you can integrate both sides. That becomes a minus natural log of TE minus T equals KT. So we move the minus sign over, take an E, you get TE minus T equals, or plus V, CE to the minus KT. So T equals TE plus CE to the minus KT, which, hey, that's what we saw right there. So separation gets you there as well with this guy. All right, so Newton's law of cooling. It's another one, and notice that it's got a little bit of the carrying capacity idea. Do you see what I mean by that?
Yeah, there's restrictions. Like you're gonna asymptote at room temperature.
Yeah, and it's like this piece right here, right? That's doing the same kind of thing that we saw with the carrying capacity, because with the carrying capacity, we had a L minus Y. So notice it's kind of that same structure of you're going to approach TE. You're going to drop to it if you're warmer, if you're higher. You're going to increase to it if you're lower. And so it's definitely got that aspect of the logistic model, the carrying capacity. Granted, it doesn't have the we're going to increase exponentially, but it's still got that limiting. And when I say limiting, I mean when you're going out to infinity, you're approaching it. And so if you ever have any situation where your rate of change has that property where, or where your population, your quantity levels out, I think Bradley said there was an asymptote, a great way to think about it. If there's a asymptote, you're going to get this structure in your differential equation, whether we're talking about population or temperatures or insert your favorite thing. And I will say this is the other thing. Now, while I kind of badmouth differential equations as monkey math a lot, this is one of the things that I do like about it, is that you can actually start recognizing the scenarios that lead to the same forms of differential equations. And so you can start going, oh, I've done this problem before. I realize that right now I'm talking about, the population of termites, but I did this another time when I was looking at salt concentration in a pond or something like that, right? Where you recognize the long-term effects, you recognize how other stuff is interacting, and it just makes it so that all of a sudden you go, oh, this is a pond problem. Like you'll hear me say that all the time. You still don't know what that means yet because I haven't shown you that example. We'll do that next time. But it's like, oh yeah, no, this is a pond problem. Oh, this is a carrying capacity problem. This is that's just how I think because I can relate it to one I've done before. So that is one of the beauties of differential equations. All right, well, I think I'm going to stop here. I know technically we got like 5 more minutes because of a delayed start. However, yeah, we're going nowhere in 5 minutes. So the plan for the coming days, turns out I have a meeting on Wednesday and I'm not going to be able to have class. I'm not going to get a sub. I know that often we'll just get a sub and all that. I'm not going to try to do that in this world. So we're not going to have class on Wednesday. I'm not sure. I haven't decided what I want to do yet. I might still go ahead and make a video. That's just me showing the topics so that you guys can watch that. I haven't decided what I want to do yet. So if I end up doing that, I will definitely let you guys know through the Canvas shell so you can know to go look for it. But we are not going to have class on Wednesday. All right, so we're not going to meet because I'm in another meeting. So next time I will see you guys is on Friday. But like I said, I'll let you know if I decide to do that. But regardless, what we're going to do next, I'm still going to show you some more examples. Specifically, I'm going to show you the mixing problems, the ones I call the pond problems, because those lead to linear first order and then just kind of march on from there. All right. So no class Wednesday, potentially a video. If I make one, I will let you guys know.
Just to clarify, we'll be seeing you tomorrow if we have physics, right?
Oh yeah. Physics is still on as normal. This is just a one-time only, happens to be Wednesday afternoon meeting that I can't miss.
All right.
Yeah, that's just one of those aberrant, weird things. It's not like I'm going out of town or have jury duty or anything like that.
All right. Cool.
Okay, well, with that, then I'm going to go ahead and stop our recording for the day and wish you all a wonderful till I see you next.